quote here, but in the book there's a quote about Louis Freeh, former head of the FBI, testifying in front of Congress about how secure DES is. And I don't want to misquote the book, because the quote of the book, although a direct quote from testimony out of the transcripts, I believe the quote he gives is ridiculous. It's something like, oh, nobody could break this in like 74 billion years, right? Which I think is a number that's completely pulled out of his ass. Even if you look at the theoretical constraints for DES, I think probably like more than that or less than that, but still, you know, far longer than anybody would care to bother. But of course, DES is not really that strong. So the goal here was, how do we satisfy all these other sub-goals about getting FPGAs into the hands of people and having people start to work on these kinds of problems, and then from there bootstrap and springboard off to their own kind of thing, but still, you know, make something that's plausible, right? And we want to have something that's a plausible target that people are going to at least assume to try in the first place. So the goal was, without doing custom hardware, we don't want to fabricate ASICs because it's really expensive to do it. It's actually more expensive per chip in small runs than it is if you were to make like an entire run of Pentium 4s. I mean, the numbers are astronomical at that point. I don't have anywhere near that kind of money. But nonetheless, it's still actually more expensive per chip than it would be if you were actually doing a huge run. We knew we weren't going to do either of those two things, right? Even $250,000, I'm not John Gilmore. John Gilmore is independently wealthy, and to him because he puts a lot of money in good places. But I don't have $250,000 to just employ 2 companies to build me a hardware machine. If I did, I wouldn't be talking. FPGAs back in the day were slower and more expensive by comparison, relatively, and less dense than they are today. And what I mean by that is they didn't have as many logic units, right? There's a lot of marketing in the FPGA universe about what constitutes performance or the availability of performance. Problems with FPGAs and rating how good or bad they are is because there is no design there, right? It's easy to say something like, oh, well, a Pentium 4 gets so many megaflops or so many gigaflops of speed, quote unquote, at a certain benchmark. You can't really do that for FPGAs because there is no hardware, right? It's just essentially a collection of logic units that you then layer your hardware design onto. So what happens is the 2 major vendors of FPGAs, Xilinx and Altera, have come up with their own market terms for how good their various lines of FPGAs are. They have various types of lines, right? They have ones that are really high performance, and those would be things like Vertex 4s in the Xilinx universe. And I think there's Cyclone 2s in the Altera universe. And then they have various other more affordable FPGAs that do less, but you know, they still have some kind of numbers for them. The problem is you can't compare the 2. If you get a number from Xilinx that says, oh, well, this FPGA is a million equivalent, that means supposedly that FPGA has essentially 1 million usable gates, logic gates, that you can use to build your design out of. But you can't look at that and then go to an Altera FPGA, and they'll say something like, this one has, you know, 750,000 logic units. But they're not transferable, right? The numbers don't really mean anything, A, because they're marketing numbers, and B, they don't actually counting the same things in the first place. As it was, I didn't have to worry about any of this because I just found the cheapest but yet most flexible board at the time, which cost me about $150, and it was a Xilinx Spartan 3 FPGA. So it just sort of made a decision for me. And that's the other thing. Hobbyists can now buy this kind of stuff in dev kits, you know, for near $0, you know, over the statistical average. And I'm going to pass around. Yeah. No. Hold on a second. Stay. So feel free to take a look at this. It'll slowly make its way around the entire room, hopefully before I'm done. And if you don't see it before I'm done, just, you know, find it, whoever has it, and then steal it from them and look at it. Just give it back to me at the end. This is a really affordable dev kit. It's essentially one board. I have a picture of it coming. And it has a bunch of things on it. One is it has the FPGA, which is what we care about. But 2, it also has some I/O. It has a serial port, a PS2 port, a VGA port, and some other things, some switches and whatnot. And it's essentially a self-contained little dev kit, right? You know, it's nothing super fancy that's going to blow your socks off, but it's enough to play with, and it's a lot of things to touch. And I'm somebody who really thinks that like having a physical component to things that are supposed to be exploratory is good, because it means you actually get to alter the state of things immediately without having to have a setup. It doesn't necessarily enter into would I use dip switches to program my desk cracker? The answer is no. But it does enter into, well, if I wanted to make it just, do little interesting, cute things, can I make it do those interesting, cute things just by flipping a switch? And the answer is yes. So again, what was the target for Cheap Crac? Well, the issue was we wanted to do as well or better than Deep Crac, right? We wanted to take advantage of the fact that 8 years of Moore's law has passed. That affects FPGAs just as much as it affects, CPUs and everything else. Transistor count goes up, right? In the case of FPGAs, what we're really concerned about is logic unit count, right? Transistors or whatever. We're really concerned about just density of logic elements on FPGAs. Notably, I should mention, a lot of people have done FPGA crypto cracking experiments in the past. One of the best papers I ever read, which is actually included in the Cracking Desk book, is by Ian Goldberg when he was still a student at Berkeley, commenting on essentially a desk cracking machine in an FPGA of the era. It was actually a CPLD, which is a logic device, and they're similar to FPGAs. They have slight differences, but essentially he found an Altera. I think it was an Altera CPLD that he could buy cheaply, that he got on a Berkeley program, and implemented a desk cracker, and then made some benchmarks off of what he found at the time. And this is written, I think, in like '93 or '92. It was a fairly early paper. So people have done this before. We didn't want to do any ASICs, like I mentioned before, and a budget of $10,000 US total for the entire project, including any overages or costs or shipping stuff back and forth to people or whatever. Now, each of these things notably only costs around $150 in the model that I bought, right? So $10,000 will buy a number of these. And we sort of expect that there will be some other costs related to shipping things and also to buying other add-on modules, which I'll talk about in a minute. But essentially, $10,000 is a lot of money person, but not a lot of money for a group of people, right? A group of people can raise $10,000 out of their pockets fairly easily if they can afford, if they can afford $150 for a board for themselves, they can probably afford to spend anywhere from exactly that amount to maybe half of that amount in a cooperative project with other people. And that was really the idea, right? How can we make it essentially micro-funded by a collective, right? Not necessarily a collective in a very heavyweight sense, just people who are interested in throwing money into a kitty and buying a bunch of stuff, and then having these things show up at their homes, and then saying, okay, here's the current state of the project. You now have a board because you put money into the pot. Let's download this stuff off of the website, and let's keep working on it. We also didn't want to have any custom boards, by meaning not just custom logic like ASICs, but we didn't want to have to create a custom board. We wanted it to be a commercial off-the-shelf development board. There's two reasons for that. One reason is you can buy them now, right? I don't have to do any work to make a development board. I have to do a lot of work to make a custom board. I have to have my design already. The other issue is that once you're done with Cheap Crac, or if Cheap Crac bores the hell out of you, you have something you can go do something else with, right? The immediate thing that when I first got, as the board moves around, people will notice it has VGA out. And one of the first things that I thought about doing when I got it, way before I ever thought of Cheap Crac, was implementing old arcade games, right? The first thing I literally thought about doing was I can implement Zaxxon on this thing, right? And not only does it have VGA, which is good, but it also has PS2, and the PS2 can either be a mouse or a keyboard. And I was like, sweet, breakout. So let me move on. So this is a picture of the board. As it comes around, you'll see it. I'm going to point out a few of the elements here. When you find it, or when it makes it your way, you'll be able to touch it and play with it. This is blown up, so I apologize for the lack of resolution. But essentially, this is the board. It's made by a company called Digilant, which is just a small little company, I believe, out of the Pacific Northwest, and all they basically do is make various types of development boards for people. They make them for industry, people who want to actually prototype, real quote-unquote hardware designs, as opposed to, My Little Toys. But essentially, this one is, this is a particular model. They call it an S3 board in their catalog. If you go to Digilant Inc., notably, if you go to digilant.com, it's some completely other different site. I don't think it's porn, but it's not what you want. But go to Inc.com if you're interested. I picked them purely because, honestly, I had a personal recommendation from a friend of mine who was looking at FPGA boards, and he said, oh, check out this site. You might find something that you like. And I looked. There are a number of other sites. I don't want to shortchange any of the other people. There's another company called XESS, which has a huge reputation in sort of the bedroom FPGA hacker community for being a guy who has put together really cool dev boards. I haven't used any of his stuff, though. This is just the one that I happened to buy. So here, this is the power. I believe this one is, I want to say that is VGA and that's serial, but I would have to actually look at them. And then you'll notice these three black connectors on the sides. These two on the top and one on the far end. Those are actually peripheral connectors for their own kind of little peripheral interface. And they make a bunch of other modules. And one of the modules they make is this little module that just includes a little USB port and a USB controller. And this just plugs in essentially to this thing. I'll pass this around also. So, the adaptability here, granted these little ports are not standard in any way. You have to buy their little boards that plug into them, and they transfer power and control and everything else. But nonetheless, you can do things insofar as you can find a board that they've made that already does it. And they have ones for USB, which is the one that being one for Ethernet. They have one that will actually do 10100 Ethernet controller on board. So you can plug this into a network and do things with it. They also have one that I believe they have one that does. They have one that does like different kinds of composite video in and out and whatnot. So there's little things like this that people have made, and frankly, it would not be too hard to they publish all the specs. Notably, the other reason I bought a dev board as opposed to making a custom board is that everything is labeled, and this is huge if you're playing with this stuff for the first time, to know what everything is just by looking at the board, right? You have a spec sheet. And you have a diagram and everything else that you would normally have. You have a data sheet for all the logic elements and all the ICs and everything on the board. But you can actually look at the thing, and while touching it, figure out what something does, right? As long as you can read English and understand abbreviations, you're pretty much well set off. Other things, there's 4 momentary switches. These are just little push-button switches that don't stay down. They're just momentary switches. And then it has 8 little flip switches. These are settable that you can use to control. These are all I/O elements, right? You have to make these do anything. They don't do anything natively, just like none of this actually does anything natively. But you can make these things do things. So one of the things I first thought about was, well, it'd be neat to have different combinations of these switches program the thing, and you might make your own little 8-bit computer or whatever. But in the context of cheap Crac, all we really care about for this right now is the FPGA, which is in the center of there, where all the traces you'll notice lead to, and that's. As this comes around, you'll see actually how big this thing is, but it's essentially the size of a postage stamp. All right. This particular model, which you can't read from here, but as you see the board come around, is an XCS 1000. What the 1000 designator means is that it has a 1,000,000 gate equivalent. They make a 250 and a 500 also, which is roughly like a 500,000 gate equivalent or a 250,000 gate equivalent. And then, oh yeah, the LEDs, of course. I always need LEDs to do stuff. So I realized that this slide doesn't make any sense. It'll make sense in a minute. As I went through this, I didn't really find anybody who had done a modern, quote-unquote, FPGA implementation of the same desk cracking project. There was the paper from Ian Goldberg. There were papers that were mostly not implementation papers, but calculation papers done in the early into early mid-90s, where people would estimate how much computing resources it would take, or what their prognostication for an FPGA would be for doing this kind of stuff. Ian Goldberg's paper actually did implement, but it was fairly old. So then I recently came across a paper by this team in Germany, and they built this thing. And the only reason I say is the Germans here is because they really rocked out, and it kind of depressed me because it's like, oh man, they got there first. But yes and no. We'll see in a minute. So this is what they built.